Okay, thanks a lot. Wonderful introduction, I think. So, all right, well, one way to start is, where are you? Any questions from last time? Totally lucid lectures, as always. Well, okay, let's see how it goes today. I'm going to take off from where we left off last time. I was building towards diffraction, right? Talked about waves, talked about the complex notation for waves. We saw how waves can add together via Fourier transforms and things like that. We started picking up on concepts of being in real space, like we are right now, and reciprocal space through the Fourier transform and so on. And that's what scattering does. Scattering is like a Fourier transform machine. They talk about fast Fourier transform algorithms. Light is even faster, so it's super fast Fourier transform. Okay. Trouble is, light does a squaring job too, and we'll get to that eventually. So today I'm going to derive the single slit diffraction pattern. This is something from sophomore physics, although I'll probably be more at the junior senior level because I'll be using the complex notation and that sort of thing. But then we're going to look at it in different ways. Matter of fact, the ways I'm going to show you to look at it, I don't see in any textbooks or anything like that. It's sort of what I've developed to develop my own physical intuition for diffraction. So that's where we're going for the first part of our lecture. And now I'm well equipped with markers. So here we go. So as I drew last time, I'm going to imagine some opaque screens. They're going in and out of the board. There's a slit between them. Matter of fact, I think I'll make the slit bigger just so my diagram will be easier to draw on. There we go. I'm going to set up a coordinate system for this thing. I'm going to put my z-axis in this direction. I'm going to put my x-axis in this direction. So right-hand rule, y is out of the board. I'm going to imagine some waves coming in. Let's draw some blue light waves coming in, right? Wavelength apart. They hit here. And right in here, the wave breaks up into a bunch of point sources. That's an important thing. It's Huygens construction, as it's called. So each one of these point sources can emanate a wave isotropically in all directions. We're going to look in the forward z direction. As we talked about last time, if we go into the forward direction, each one of these little sources will give us a phasor. Remember that? Each phasor, since the path length is the same, each phasor will be in the same direction. We'll get a constructive addition of the waves, and the total field would be proportional to the width of the slit. Right? Okay. I'll put in a few more things too. I want to put some dimensions here. I'm going to put minus a and a plus a. So the width of the slit, W, is 2a. And my origin is right here. But now I'm going to go off the axis. I'm going to shoot down at an angle and start putting my paths down towards some detector at some angle here. Some angle theta, and paying attention to where the origin is, I'm going to also then draw a line right through the origin, like so, as sort of my equal, my fair line. Everybody's perpendicular to this line. We can see that the wave that takes off from the origin is ahead of these guys, right? These guys have to go an extra distance. On the other hand, it's behind these guys who are in front. So there'll be path differences that will cause these phasors to be at different angles, and we're going to have to sum them up. All right, let's do that. Let's come up here distance x. Right. Let's look at the light that goes to the detector. Let's remember our equation for a wave. I'm going to get rid of these vectors. So let's remember the wave is proportional to I, K, dot R, right? And let's remember that K is 2 pi over the wavelength of the light. So we're propagating off in this direction. We've got a K vector in that direction. So we don't need the dot product. We're going to go in that direction. And the field clear down here at the detector, let's put a little break. All right, long distance. Here's our detector. And all these different waves meet at the detector. So for the origin wave, we'll say the distance is r, capital R. For these other waves, there's path differences. And right here at x, now I'm going to draw a very tiny little line. Right here at x, we've got an extra distance. And if you look at this, if this is theta, where's theta over here? And it's right in there, you see it? So there's a theta sitting right there. And you can kind of see that because, of course, if you bring this up to 0 theta here, that'll collapse to 0 as well. So you can see we got a right triangle now. X is the hypotenuse, so this distance right here, this thick black line is what? Very good, class. Sine theta, right? So it's x sine theta. So down here, I'm going to have a whole bunch of waves. I'm going to have waves between x minus a to x plus a. I'm going to have a whole bunch of waves. And in general, they're going to look like e to the I, k. They're all parallel. So I'm going to have an r, but I'm also going to have this factor x sine theta. You see that? Everybody's traveling at least r relative to the origin, but some have extra x's and have a little bit less x. That's an important step right there. All right, well, if you're good with that, that's wonderful. Notice this term really doesn't much matter. If I move the detector, it changes. If I don't move the detector, it doesn't. That's not what's interesting to us. It's this here, because I've got to add up all these phasors as a function of x. So I'm now going to blow off this term. I don't care about this guy anymore. And I'm going to just economize and say e to the I kx sine theta. That's for 1x. I've got to add up all these waves. You know how I'm going to add them up? With an integral, right? So the total out here at the detector is the integral e to the I kx sine theta, integrating over all x from minus a to a. Now, as I alluded to last time, there's a few directions I can go right now. One direction I want to go is stress this Fourier transform going on. I've got a limited integral from minus to a, but I could integrate from minus infinity to plus infinity if I put in the transmission profile. So let's just do that for completeness. And I'm going to do a subtle change here. Because I want to. I've got an agenda, all right? All right. So this is starting to look like a Fourier transform. We're Fourier transforming the transmission profile of that slit with this term here. Notice there's the space variable, and here's why I did the little change. See that? That's my reciprocal space variable. Okay. I'm going to call that something. I'm going to call it Q prime. I'm going to put a little prime on it because when I get to 3 dimensions, I want to call it Q, and it'll be slightly different, all right? So I guess come up here, complete the board. I've got at the detector, I've got the transmission profile, I've got e to the I q prime x dx, where q prime is k sine theta. And of course, that is a Fourier transform. The field, you know, I'm a bit remiss now. Let me doctor this up a little bit. Right, that helps a lot, I think. I've transformed from x space to q prime space. The units of x are meters, centimeters, miles, right? The units of q, right, are inverse length, right? So I've transformed from one space to the other. And in x space, a bit of repetition from last time, in x space, I've got some transmission profile that looks like this. In q space, we've done this integral already. Now, I'm not going to do it again, right? We've done it already. It was that sinc function. And in q space, or q prime space, q prime, we've got this function. And those two, and let's remember what this is. This is the field. It's not the intensity. It's the field, right? The field and the profile of the diffractor are Fourier transform pairs. There we go. Let's keep pushing this. Minus a. Where's the first minimum over here? Let's remember the function. It was sine of u over u. What will u be? U is q prime a dimensionless variable, right? So I've drawn q here. Maybe I could first back off and make it a little easier on us. If it was the dimensionless variable u, what's this point? Pi, right? Matter of fact, I think what I'll do is maybe doctor this up a little bit. Let's get rid of all this stuff.
On your transmission profile, that function had a height to it.
Yes.
What's that mean for this physics, or does it have to mean?
I'm glad you asked that. I'm going to get there. Let me handle the horizontal dimensions first. I think last time I called it capital C just arbitrarily. So let's draw this sinc function in a grander scale just so that I can do a lot of things with it. So if we are in this dimensionless space, this point is pi minus 2 pi, etc., right? Let's look at it from other perspectives. What if we go to q space for q prime? It's got the same shape. But what's this point now? Well, I guess we just solve, right? We just solve. So q prime equals pi over a. And here's minus pi over a. So those are our first minimum, right? If we're really dealing with an experiment and we're in the laboratory, we need to know the angle, right? So we ought to do that. let's see, what was Q prime? Q prime is K sine theta. So the first minimum is when K sine theta equals pi over A. So solving for sine theta, I got pi over A, and that would be inverted lambda over 2 pi, correct? And then of course we get lambda over 2A, which is lambda over the width of the slit. So here we go, like so. So that's lambda over W. And of course, that's the answer that we typically remember when we talk about diffraction. So there's three different perspectives on the whole thing. Now that's you might say the horizontal perspective. There's a vertical perspective here. This is height C, and if I remember correctly, and you can correct me if I remember correctly, you can correct me if I'm wrong. This was 2CW, wasn't it? Or else 2CA, I forget. CA? Thank you. So that actually makes a little more sense, W, doesn't it, at CW then, right? Good. Okay. Now, let's get physical. We can't detect the doggone field, you know. It's too bad we can't. Actually, with holography, we kind of can. We beat it against a local oscillator or something like that. But in most experiments, if we're just shining this on the wall, we're getting the field squared. So let's remind you that intensity is proportional to the field squared. So let's square this thing. And if we square it down here, we then get this shape. All right. Again, fortunately, the horizontal stuff doesn't move. We've got pi over, oops, I want to be in real space here. Lambda over W, right? Let's also remember sine theta, but very often the angles are so small that we approximate sine theta's theta in radians, correct? So, but something neat is happening here. When we square it, what's the magnitude? C squared, W squared. And that means that if we open the slit twice as much, the forward scattered intensity, or I slipped, didn't I, right? I slipped. You can tell on the light scatter, okay? The forward diffracted intensity quadruples. And that doesn't make any sense at all, does it? Because, it should double, right? But what else is going on when you open the slit by a factor of 2? You open the slit by a factor of 2, you get 4 times as much light. What else happens? Gets skinnier by a factor of 2, and the total area under the curve only increases by a factor of 2. Right. Here in this room in St. Louis, Missouri, we nearly blew the conservation of energy. Oh my God. But there's more. So I guess then the sinc function gets squared too, right? Sinc squared of u sine u over u squared. What does that look like in the limits? What about when u is much less than 1? Somewhere in here, right? Here's u, somewhere in here, right? Well, that's an easy expansion. Intensity would go as u minus, remember the next term? Right? Which is 1 minus u squared over 6, correct? And when you square it, what's that going to be? You know your binomial theorem? I'm not sure what they teach engineers these days. 1 minus u squared over 3. So that's kind of an interesting result. And later on, we're going to call that the Gounier result. I'll call it that right now. What the heck? That's Gounier's expansion at small u. We'll revisit this when we get into scattering from particles. What about the large u limit? And notice what I'm doing. I got a function, I'm playing with it, right? I'm trying to get to know it. What about the large u limit? Well, we can do that too. Let's slip off to the... There's a math professor at Kansas State. I've never seen him lecture, but I've had numerous students tell me that I'm thinking of this because usually you go from left to right, and now I'm going from right to left, you know, but what the heck. And this guy apparently erases as he goes. You can see I'm not even hand-eye coordinated enough to do it, but this guy can do it. And I guess it drives the class nuts. There'd be this whole bunch of math, and it'll be vacant here, and the, sort of the math moves with him as he... Okay, so where was I? Well, so I was going to look at the large u limit, and that's pretty easy to do too. So if we go over here, let's see, when u is a lot bigger than 1, we would have, well, we'd have just this, wouldn't we? We'd have sine squared u, which is positive definite, over u squared. I guess that's pretty simple. And of course, that means we've got something that looks like this, right, times u to the minus 2. So it's decaying away. It's a power law. How should we plot a power law? To make it look like, I mean, okay. Here's the way, so in Kansas we have this great rivalry between University of Kansas and Kansas State. So usually I make a joke now. At KU, they would do it this way. They would plot it linear. They'd plot the intensity versus u in a linear fashion. You would have this u to the minus 2, and there'd be this ripple pattern underneath it, right? But at Kansas State University, we understand that power laws can be displayed if we plot how? Log. So let's do that. We'll make both axes logarithmic. So to emphasize, we got log u and log intensity. And remember, you never get to 0, right? So you can just go forever like this. You can go 1, 1/10, 100th, 1,000,000th, right? And you got the same number all the way, right? So it's important to recognize it's going to be flat for a while, right? Then it's going to curve over, according to Gounier, with some sort of quadratic dependence. Then it's going to dive bomb to 0, right, which comes off the graph, but that's at in a u space. Right? That would be when u equals this. Okay? Then it will come back up. Right? And there'll be, it's important enough for me to pull out the red marker. There'll be a u to the minus 2 envelope. And that's the way to look at one-dimensional diffraction. I slipped in another term, didn't I? Right? I started off calling it single slit diffraction. Now I'm calling it one-dimensional diffraction. Well, we should remind ourselves that we've got the Gounier regime here, and we've got the intensity going as CW squared. You might call that the volume of this one-dimensional object squared, right? These characteristics are going to show up in n dimensions. One-dimensional diffraction, two-dimensional diffraction, three-dimensional diffraction, and if we lived in alternative universes, n-dimensional diffraction. We'll stop at 3. All right. Let me see where I am. While I'm seeing where you am, you can think of any questions you want to do, because there we go. Any questions? Okay, now I'm really going to take you away from standard stuff. I think what I'm going to show you now is just my invention. All right, it's not published anywhere. I'm going to keep looking at this problem. I might keep these up. Let's clear up as much of the board as possible. What are the units of q prime? Inverse distance, yeah. So what are the units of inverse q? Distance, yeah. That's going to take us somewhere. So what I want to do, I'm going to draw a profile of the slit again. So here's my transmission profile. And you'll recall that when we were in the forward direction, all the phasors added up in the same direction. But when we went out to the first minimum, or started working our way out, the phasors started pointing in different directions. And it's the sum of these vectors, these phasors, that determines this. Right? Here they're all pointing in the same direction. Here they've managed to point in enough different directions that they're summing up to 0. As a matter of fact, the first minimum is a rather special point. I think I'll get rid of these two and draw a little phasor diagram here. So right here, I've got a bunch of phasors that are all pointing in the same direction, like so. But out here at the first minimum, they've managed to point in a complete circle. So maybe to do this, I could start off by saying, okay, here's one, here's another. And this is called a vibration curve. You can find this in junior level optics books and things like that. But the point is, it came around, so the total is 0, and that's the first minimum. Okay. So if I look over here, right, I've got a bunch of phasors from this transmission profile. If I break this apart, I've got some phasors that, remember, a phasor came from this edge of the slit, a phasor came from this part of the slit, a phasor came from the middle of the slit, right? And so I'm going to try to represent those phasors. So I'll put one phasor here, and then I'll work my way in. There'll be a phasor, but it won't be parallel. It'll be tipped up a little bit. And by the time I'm to the center, I'm flipped once around. I'm flipped halfway around, okay? And I'm going to keep going. My diagram isn't going to be perfect. And then by the time I'm to the other side, I'm like this, right? So, and that's what happened here, right? I went around, right? Here's the center, right? And then I came down, and I came back in the same, and those add up to 0. And then I'm going to remind myself once again that This is the first minimum, and that Q prime has units of inverse length. Now, and Q prime, let's see. Q prime, so this is, so I'm thinking out loud here, because I'm not entirely sure how to do this. So I'm at the first minimum, Q prime A equals pi, Q prime equals pi over A. The length scale, Q prime, getting messy, Q prime quantity to the minus 1 is A over pi, right? At the first minimum, I've got a length scale of A over pi. Okay. So if I do a little algebra, and it's not obvious why I'm going to do this until I do it. But if I do a little algebra, pi over Q prime equals A, so that 2 equals the width. So this length scale, 2 pi over Q prime, is the width of the slit. Two pi over Q prime. Let's get rid of the 2. Is the width of the slit. When Q prime equal to 0, how big was Q prime over 2A, or 2 pi over? At Q prime equal to 0, how big was this? Infinity, right? And then we started going to bigger Q prime values, right? So this started getting smaller, right? But it still wasn't as small as the slit. And so the scattering didn't change much, did it? I erased my logarithmic plot. Okay? So here I go. I'm cranking along in Q prime space, and I'm still nowhere near 2 pi over Q prime is still humongous compared to the width, and nothing happens. And as I keep cranking up Q prime, this width gets smaller and smaller until finally I start to see the slit, right? It's like with small Q prime, my resolution is poor. But as I start cranking up, going to bigger angles, that's how I do it experimentally, right? If I start cranking up Q prime, this inverse length of Q prime finally starts to sense the slit. And at the moment that this particular combination equals the width of the slit, boom, right? Goes to 0. Here is Q prime equal 2 pi over the width of the slit. So you start getting an intuition here that Q prime, its inverse, really is a length scale of the diffraction experiment. When the length scale is much bigger than the thing that's diffracting, it can't tell a slit from a rough hole, right? It's like the resolution isn't good enough. But as we go to bigger angles, make Q prime bigger, inverse Q prime gets smaller, and we start to see things. And it repeats, right? After a while, this collapses even more, goes through minimum, things like that. We start seeing more and more. Here's an interesting question. What is happening as we go through these lumps? Let's draw a little picture of that. I think we can get rid of this. Let's draw the slit profile again. Let's suppose that 2 pi over q prime now is only that big. So let's remember, look at this. Every little hunk of 2 pi over q prime has a whole series of phasors that add up to what? You see it? Right? So right in here, we got a whole spin around, right? We got all the phasors adding up to 0. Matter of fact, if we go over another one, and another one, let's suppose these are all 2 pi over q primes, right? We got phasors adding up to 0. Nothing is contributed from these center regions. But look, there's a little bit left over on the edges. So as we are working our way down this power law of -2, right here we've managed to fill one of these q prime regions into the slit, nothing gets kicked in. But then as soon as this just collapses a little bit more at bigger q prime, the edges start to kick in. See that? And then as soon as there's 2 of these regions in there, we go through the second minimum. Then we collapse it. You see what's going on here? We went through 3 minimum. We're just past the 3rd minimum, and the edges are kicking in. And so now what we've got is the concept that the stuff out here is diffraction due to the edges, and the stuff in here is the whole ball of wax. So a guy named Porrad realized that a long time ago with three-dimensional objects. Here we're seeing it with one-dimensional object, the slit, and the fact that this power law here, this u to the -2 power law, is often called the Porrad regime. Well, this is never called the Porrad regime because nobody ever looks at single slits this way, but they do look at three-dimensional diffraction this way. It's called the Porrad regime, and it's related to the surface of whatever's diffracting. Now with my slit, of course, the surface is just the edges of the slit. But when we get to a sphere, it's going to be the surface of the sphere. And I'm trying to lay a foundation. Okay? Porrad doesn't do this 2 pi over q prime stuff that I'm doing.
So why do the q, so at the first minimum, obviously phasors make a complete circle. The second minimum makes 2 complete circles. Why is it rearranged so it's the edges, not the middle there?
Because I made it do that.
Okay.
Good question. Okay? He's right. I could have well, if I had 2 of them, I could have just popped them out like that and said it was the center. Okay? But arbitrarily, I squeeze them in like that and say it's the edge, and then indeed if I do that, I can show eventually that it's related to the surface. Now I'm not going to show that. I'm just justifying the surface right now, showing it is more complex. Good question, as always. Okay, I'm going to shift gears. I'm going to continue this. You might notice I'm not talking about cross sections and polarizations. I decided to keep just charging through into Q space. That's where I'm going. Okay, for continuity, then we can pick up some of this other stuff later on. I've got 15 minutes. I want to do some more, but I want to make sure this is in your brain. I'm going to take after this. Any more questions? It occurs to me I have a handout or two. Where I put them, I don't know. Not there. All right. I want to go to 3 dimensions. So we've laid a conceptual foundation. We're really not interested in slits. We're interested in diffraction from 3-dimensional objects. That's the foundation of scattering. That's the non-electromagnetic foundation, but it's the foundation. But to go any further, I got to generalize what we've done here. You might recall when I did the slit, I put a whole bunch of little point emitters inside the slit, the sources of Huygens wavelets. I'm going to do the same thing now. I'm going to consider a 3-dimensional object, an arbitrarily shaped object. There it is, okay? I'm going to use the methods of calculus. I'm going to break this up into a bunch of small volumes. So I've got a dx, I've got a dy, I have a dz in some manner. I get a little dv, right, differential volume, okay? A lot of you don't know it. This d stands, it's Italian for de little bita, okay? So de little bita volume here, okay? You can laugh whenever you want. Thank you very much. And basically this then gives me a whole bunch of these little, they're so small they're points, these differential volumes, right? And so that's what I'm going to do. I'm going to erase this right away and replace it with what I like to call a system of scatters. So here we go again. I'll draw some arbitrarily shaped particle, and I'm going to put a bunch of point scatters in there. I'm going to put them in uniformly. I'm not going to draw them all. And you want to know why? Because there are an infinite number of them. We'd be here all day. And put in a coordinate system like so. One of these point scatters is at a position vector r, okay? The light comes in and totally permeates the particle. I don't care how dark and opaque it is, that's the first thing it does. And it's related to something called the Ewald-Oseen extinction theorem. If not that right now, let's remember I'm just trying to do diffraction. My index refraction is very close to 1. And it has no imaginary part, so there's no absorption. So my wave will go all the way in, right now. Do the first things first. So the wave, the incident wave totally penetrates that. Let's get a blue laser here, shine the light in, and we're going to give it some wave vector k incident, like so. The light hits one of these point scatterers, scatters out to the detector. So there's a detector clear out here a long ways away in the so-called far field. Distance is great compared to the wavelength and the size of the particle to the detector. And let's remember the key thing here is to keep track of the phase of these things so we can add up. Here again, I'm just looking for the proportionalities. E to the I k dot r. So that's our wave formulation. So right here, the wave is e to the I k incident dot r. Okay? Here comes the hard part. It's going to scatter up to the detector with the different wave vector. And we're going to call that K scat, okay, for scattering. We're going to assume elastic scattering, so the magnitude doesn't change. The wavelength doesn't change, so the magnitude doesn't change, but it's in a different direction. Certainly, it's a vector. So to figure out the wave at the detector, we have to account for the fact that the wave came in and was equal to this right here. But then some more propagation happened. It went to the detector. So we got to handle that. So we got to know where the detector is. Okay, I can do that. It's up here at R. And notice I drew parallel light because they're going to meet. And this wasn't a light beam, I'm sorry, parallel vectors. So if the detector is at R, and if the little scatterer in this system of scatterers is at little r, this distance is what? Yeah. It's big R minus little r. So here's the wave right here. This algebra represents the wave here. Then this happens. Some more propagation happens. So here's some more propagation. K scat, right? Dot product with the vector that it propagates along. So that's a crux move right there in this derivation. Now I'm going to rearrange terms. Now it's algebra. I'm going to pull out the position vector of the detector, much like I did before. I don't really care where the detector is. What I care about is where all the little point scatterers are. So e to the I k scat dot r, and who cares? And then e, let's see, I've got k incident r, and notice the minus r here for k scat. So I got I k inc minus k scat dot r. There it is. Okay. That's the system of scatterer terms. And I forgot my little vectors here. There we go. We now have a new parameter, right? We got this vector difference. Let's take a look at it. We've got k inc. We've got same length, because the wavelength didn't change. K scat. And it's the difference of these two. So whatever this is, I'm going to call it Q. Whatever this is, if I added Q to K scat, I would get K incident. So Q is right here. By definition, it is and this came off at some angle, theta. So there's theta. So if you dropped a perpendicular, you could see a sine relationship to half the angle. So it's pretty easy to show that 2k, now since these have the same magnitude, I'm going to represent them as k, 2k times sine of half the angle. So this is the all-important scattering wave vector. So we're at the end of the hour. But what are we going to do? what did we do with the single slit? We found the phasors, remember, as a function of x only, and we added them up, right? We now have phasors like this. We now have phasors that look like this. And R represents the position of all the little dVs that make up the particle. It could be my hand, right? So, how are we going to add them up? With an integral. Going to add all these up, right? We're going to integrate over all the positions of these guys. And we could define a density function. The density of these point scatters, right, in three-dimensional space. So we've got to do this over, well, maybe there's two ways to do this. Let's do this. Let's put just nothing here. We'll integrate this over the volume of the particle, or whatever it is that's doing the diffraction. Or we could integrate over all space of the density function, where the particle is and where the particle ain't, right? Just like with the transmission profile. But in either case, especially in this case, what mathematical form does that have? It's a Fourier transform. So I'll stop here because I'm supposed to stop after about an hour. I guess I've been going for about 50 minutes. But here's a homework problem. Do this for a sphere. Now it will help, I can help you. The first time you do this, you stumble around a little bit. The coordinate system you want to use is to have your light come in from the negative z-axis so that theta is right here, right? Right-handed system, okay? So phi is right here. So you want, if you're going to do a sphere, you're going to do your delta volume for a sphere, or another terminology would be this. Actually, these are identically equal. So there's a bunch of ways to write this. But regardless, they're all equal to r squared dr d phi d cos theta. So if you use that and integrate over cos theta from -1 to 1, phi from 0 to 2 pi, r from 0 to capital R, the size of the sphere, it will be a good exercise for you. Matter of fact, when you get the solution, break it into a volume part. Pull out 4 pi r cubed over 3. Pull it out and then leave behind the rest. Then square it. You'll see the volume get squared. Remember how the width of the slit got squared? Expand the rest of it for small u. Look at it at large u. Do everything I did with the slit. If you could do that between now and tomorrow, I think then when we talk about it tomorrow and I'll kind of flesh it out, then it'll really sink into your head. And that's the Fourier transform and then squaring it of the sphere is foundational to the light scatter. So that would be just great if you did that. All right. So I'm done. I guess, though, we have time for question and answer.
So I have a question, maybe to basic for experiment. So we normally plot it in Q space, but Q is what? 2 pi. So
Well, should we go back? Should we go back to the single slit?
yeah. I mean, so when we do experiments, normally we will change the theta or change the wavelength to get those kind of.
So now you're talking about actual scattering from
Yes,
stuff.
actually.
Okay. Yeah. Where we're going is we're going to plot versus Q. So so when you do this homework assignment and you figure out the diffraction from a sphere, if you plot it, intensity versus angle from 0 to 180 degrees, and I'll just start naming this mark as a little faint. This diffraction limit is often called the Rayleigh-Debye-Ganz limit. But if you plot it for different sizes, if the size is really small, it's isotropic scattering. And that's specified by what's called the size parameter. All technical people, if you say, oh, it's really big or oh, it's really small, immediately respond relative to what, right? Yeah. And so the size parameter handles that. It's k times the radius of the particle. It's 2 pi r over lambda, right? It's comparing the particles. So this would be for a size parameter kr less than 1. You start cranking up the size parameter, though, the scattering in the forward direction becomes more dominant, a little bit. And then when you start getting size parameters of 2 or 3, I forget exactly, you actually then start getting some bumps, like so. And the bigger your size parameter, the more your bumps, right? I guess I put that below 0, so I shouldn't do that, okay? So that's if you plot linear intensity versus linear angle. You could put, a lot of people will plot log intensity over here, so then you can keep watching what's going on. On the other hand, if you plot this versus Q, and if you plot it log, and log intensity, then you're going to get something that looks like, you're going to love this. It look familiar? Qualitatively, it's the same shade as single slit diffraction. Quantitatively, it's a little different. These minima aren't at lambda over the diameter. They're slightly different. I think it's 1.43 lambda over the diameter. Okay? This envelope is not, oh, and I should point out, let's be smart and plot this QR, dimensionless. Okay? Yeah. So if we plot QR, this versus QR, all these size parameters are here. But the small size parameter will only be here, right? The next biggest size parameter will do this, right? And big size parameters will go out to here. You see what's happening? But by this dimensionless variable, they'll all collapse together. You see, and that's got to give you satisfaction. The plethora of things out in the world, if you can unify them in some manner so that they all look the same, then you're really allowing yourself to unify things and perhaps develop your understanding. So it's extremely important. This slope out here is QR to the -4, not -2. Okay? Now, the secret is this will always be QR to the minus dimensionality plus 1. So the slit was one-dimensional. The sphere is three-dimensional. Circular apertures, so this works for circular apertures. It'll look exactly the same. The minimum will be at 1.22 lambda over the diameter of the aperture. You probably know that. And then the slope, of course, will be minus 3. So that's the foundation to what I call Q-space analysis. And then when you start cranking up the index refraction, this changes